Hello students, and welcome back to another lovely day of physical science. In today's lesson, we are going to learn how to properly measure. So the learning outcome for today is I will be able to accurately measure mass, length, volume, and temperature using what are known as significant figures. Significant figures are one of students' favorite things. You're absolutely going to love it, especially when you get to like 11th grade chemistry or 12th grade physics. It's kind of a big deal. Because in science, we really want to be as accurate and precise and detailed as possible. And that's what significant figures allow us to do. But before we can really get further into significant figures, we need to talk a little bit about the different types of measurement that we'll do in this class. So there's volume, and volume is just the amount of space that an object takes up. So, you would have your own volume because you're taking space. Or if you picture like a 2 liter of soda, well, it's because the size of that bottle takes up 2 liters of space. Length is just the distance between any 2 points. Mass is the amount of matter in an object. So that is, it's almost like how many atoms there are per a certain size. So it's how much matter there is. Time is the period between two events, and then temperature is a measure of how much energy, atoms or particles have. So before we get further into that, we just need to quickly recap on place values. So place values, if you just picture this as like a generic number line, so here we have these different x's, your decimal, and then place values going behind. If we look at this x right here, that is what we call our ones place. Over here is our tens place. If you picture the number 10 being like 1, 0. We'd have our hundreds place because 1, 0, 0. And then our thousands place because 1, 0, 0, 0 would be 1,000. After the decimal, we have our tenths place, our hundredths place, and our thousandths place. And those are going to be important to remember as we go through these notes and learn how to properly measure in science. So, measuring using significant figures. Significant figures are used to show the accuracy in a measurement. So it really is important, depending on the device that you're using, for how you measure and what number you record. So accuracy depends on the smallest increment shown on the measuring tool. That is, if it's a meter stick, balance, glassware, thermometer, etc., you really have to look at what is the smallest increment, and then the last decimal place is going to be an estimate. And again, this will make more sense as we go through some practice examples. But really, the more decimal places that there are, the more accurate that the measurement is. For example, looking back to this slide, if you have a measurement going to the tens, well, it's far less accurate than if you have a measurement going all the way to the thousands. So, steps to properly measure using significant figures. First thing you want to do is find the smallest increment on the measuring device. Then, you just want to estimate exactly one place value to the right, always. I can't stress that enough. You always, 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 always have to estimate exactly one place value to the right. For example, if your smallest increment is to the ones, you would have to estimate to the tenths. If your smallest increment was to the hundredths, you would have to estimate to the thousandths. And again, we will get practice with this coming up here. So, step number 1, finding the smallest increment on measuring device. Here you have this nice blurry pencil, and then you have a meter stick down here. When you're doing this, we need to find what is the smallest increment on this measuring device. Well, if this is 7 and this is 8, and we have these increments right here, we want to find out, what decimal place does each small line represent. Well, if this is 7 and this is 8, we have 7.1, 7.2, 7.3, 7.4, 7.5, 7.6, 7.7, 7.8, and 7.9, and then we would finally hit 8.0. Well, you'll notice from each one of these numbers what's changing. Well, it's your tenths value. You're going from 0.1 to 0.2, 0.2 to 0.3, 0.3 to 0.4, and so on. So therefore, looking back at our number line, what does each small line, that is, what is our smallest increment? Since the tenths place changes, the tenths place is the smallest increment. So there we go. We have now found that our smallest increment, so step number 1 to measuring properly, our smallest increment is the tenths place. So let's go on and practice step number 2. Step number 2 says, estimate exactly one place value to the right always. So remembering back to the previous slide, our smallest increment was the tenths. So if we want to figure out what place value is to the right, well, it's just going to be our hundredths. So when we're measuring with this measuring device down here, it's telling us that no matter what, we have to measure to the hundredths place always, every single time, because the smallest increment is the tenths. So we have to measure to the hundredths. Now step number 3 is really just writing it down, I guess. So for this, I would like you to please pause the video and try this on your own and figure out what is the length of this pencil. All right, now that you have had a chance to try this out, as we talked about in the previous slides, your answer had to go to the hundredths. It had to, because that's what this measuring device is doing. So if your answer is going to go to the hundredths, your correct answer is 8.24 centimeters. And if you got that, fantastic. And we'll actually talk about it on the next slide here. So taking a look at this device again, we know we have 7.1 and 0.2 and 0.3, so those would be 8, 8.1, 8.2. So we know that the pencil is longer than 8.2, but it's less than 8.3. So we need to estimate somewhere between 8.2 and 8.3. So we estimate to the next decimal place. And again, it's an estimate. If you put 8.25 or 8.23, that'd be okay. You know, if you said like 8.29, it's definitely not, you know, super close to this 8.3 line, but the last place is an estimate. So that's really what you're doing, is you are telling other scientists, hey, I know for sure that we're between 8.2 and 8.3. And I'm thinking it's it's pretty close to halfway, but a little bit less. So I think 8.24. You are telling other scientists that this last number is an estimate, but you know for sure you're between 8.2 and 8.3. All right, so let's see what happens if we have the same amount of water, but we use a different measuring device. That is, we have different increments on the measuring device. So here we have 3 different graduated cylinders, but notice they all have the exact same amount of water. The difference is the increments on there. This one goes from 0 to 1. This one goes from 0 to 0.1 to 0.2, 0.3, and so on. This one has even smaller increments, so like this would be 0.71 and 0.72 and 0.73. So you can see the importance of needing to accurately go to the correct decimal, because otherwise you're lying to other scientists about how accurate your device was. So let's go through and talk about this. So here we have those 3 graduated cylinders again. And let's take a look at graduated cylinder A. So each graduated cylinder has the same amount of water, but is going to be measured differently because of the increments that are on that graduated cylinder. There's no increments between 0 and 1. So we're not going to get a very accurate answer for graduated cylinder A. It's just, we can't, because we are really ballparking in here. We are really estimating somewhere between 0 and 1. So our smallest increment in this case is the ones place. So if we're going to estimate one place value to the right, well, we're going to be estimating to the tenths. I think that this water is clearly closer to 1. So I can estimate as being like 0.7 or 0.8. You know, I'm not really sure, but I just know it's a little bit closer to 1. So I might estimate this to be 0.8 milliliters. Again, it's an estimate. I don't know. It's really hard to tell other scientists with accuracy or with confidence that I'm more accurate than that. Okay? Graduated cylinder B now makes it a little bit easier. Increments are going by the tenths. So our smallest increment is the tenths, which means we are going to estimate to the hundredths. Well, we can see for sure now we are between 0.7 and 0.8. This helps a ton. Since we are now for sure between 0.7 and 0.8, we have to estimate to the hundredths place. So I might estimate this because I think it's closer to 0.8 than to 0.7. I'm going to say 0.78 milliliters. Okay, and now for graduated cylinder C. And you can see our answer is going to be even more accurate with this one. So now our smallest increment is increasing by 0.01. So this line is 0, 0.01, 0.02, 0.03, 0.04, 0.05, all the way up to 0.1. So we have a lot more accuracy now. So our smallest increment is in the hundredths place. So we need to estimate to the thousandths place with this graduated cylinder. And now when we look at that line or that meniscus again, so the bottom of this, we can see right here, it looks like it's right on this 0.77 line, but we actually need to indicate we have to go to the thousandths because we are talking about the accuracy of this measuring device. So we still have to estimate one place value further. So I would estimate this as 0.770 milliliters. So on graduated cylinder C, 0.77 milliliters would be an incorrect answer. You could not simply say 0.77. You have to say 0.770 milliliters. And I would like you to please pause the video and take a moment to think about why. Okay, so to give you a little bit lengthy of an explanation here, 0.77 milliliters would tell the reader that the smallest increment was to the tenths. That's what you'd be telling. You would be telling other scientists, hey, my graduated cylinder was this one right here. So all I can see is that I'm between 0.7 and 0.8, but I don't know anything in between. But since graduated cylinder C does have these smaller increments, and you can say for sure, like, hey, I know it's definitely 0.77 and maybe up to like 0.78, but I really think it's right on this 0.77 line. So I think it's 0.770. That zero is telling them that, hey, I really think it's right on that 0.77 line. And so that's the difference between 0.77 milliliters and 0.770 milliliters. So again, notice that even though we have the same amount of water in each one of these graduated cylinders, our answer changes based on the number of increments that there are. So you always have to find your smallest increment and then estimate just one place value further.